So let's do just some math, just basic math about covariance estimation. So let's say we have an ensemble of capital N forecasts. They are used to estimate the sample covariance matrix B tilde. So this formula is really the traditional formula to estimate, to have an unbiased estimator of the sample covariance. And here, delta x BP is the pith ensemble perturbation. So it's the difference between the member, the pith member, and the mean, the ensemble mean. And we will define another object, which is the asymptotic sample covariance. So it's this B tilde star, which is what we would get with an infinite ensemble that we don't have, but that's our target here in this section. So since we don't have an infinite ensemble, our estimation of B tilde is affected by sampling noise. So it's just the difference between what we get and what we would have with an infinite ensemble size. It's important to have in mind that the sampling noise strongly depends on the ensemble size. So here it's just a very simple experiment with a 1D system where I defined a true covariance matrix here on the left, and I took its square root to randomize it and define an ensemble with here 10 members in the middle. And on the right, I compute the sample covariance computed using these 10 ensemble members. And we can see some structures of the diagonal, but we have also a lot of noise compared to the panel, the left panel. If we increase the number of members, here 20, 30, 50, we see that the sampling noise is reduced and we get closer to the true solution on the left. And so if we have 1,000 members, well, we get back to the true covariance. So a simple solution to have very precise covariance estimations would be to have very, very large ensembles. But for the big systems that we have, it's not computationally possible. So the solution will be to use some filtering to get rid of the sampling noise. Another thing I would like to mention is the sampling noise properties. So the sampling noise that is affecting the covariance matrix is not completely random because it has some structures that are linked to the true covariance. Here, in this example, on the left, we have the true covariance matrix, and it's completely homogeneous. The variance, the diagonal, is constant, and the length scale, which is the width of the function here, is constant too. And I compute the sample covariance with 10 members here in the middle, and I just do the difference to get the sampling noise on the right. There is no specific feature for this sampling noise here on the right. In this second example, I have an homogeneous length scale, but a heterogeneous variance. The variance is smaller at the bottom left, and it's higher at the bottom left and smaller at the top right of the true covariance on the left. And we can see that the sample covariance in the middle have the same kind of structure. And if we do the difference, actually there is less noise at the top right because the original variance is smaller. So the sampling noise amplitude is related to the asymptotic variance. Here it's another example where the variance is homogeneous, so it's a constant diagonal on the left, but the width of the function, its length scale, is not homogeneous. It's broader at the bottom left and tighter at the top right. And we can see that the sample covariance has the same kind of structure, and that the sampling noise also exhibits the same kind of structure with wide and smooth structures at the bottom left and small scale structure at the top right. So the sampling noise length scale is also related to the asymptotic length scale. That's very important because when we want to filter the sampling noise, it's important to know what are its structures. So the common technique to filter the sampling noise on a covariance matrix is to do localization. So we do a show product, so it's an element by element matrix product with the localization matrix L here. So basically Bij is equal to Lij, the localization term multiplied by the sampled covariance matrix B tilde Ij. And in practice, we will use a L matrix that damps the long distance correlation that are small in general and that will be more affected by the sampling noise. So that's why we call it localization. So at the bottom, you can see the sample covariance on the left with 10 members, the localization matrix L with a given length scale 0.1 here, and the localized covariance on the right. So it's basically the product of the previous two. And we can see that it's a lot better than the raw sampled covariance on the left. We have removed most of the noise and we can keep some of the signal. So now the main question is, okay, what is the optimal length scale for the localization? And it's really critical to remove the sampling noise while keeping most of the relevant covariance signal. So here we start with no localization because the localization matrix in the center is 1 everywhere. But progressively, we will use shorter length scale. And when we are at 0.1, it's good. We have removed most of the sampling noise on the right. But if we get smaller length scales for the localization, well, finally, we are losing the interesting signal of the sample covariance. So there is no more noise, but, well, there is no more signal neither. So it's not really interesting. And so the question will be how to get the optimal length scale. We can also add a new term, so combine an ensemble term and a static term. So it's what we call hybrid covariance modeling. And for here, an example with an homogeneous static B, the BS green term here. On the left, we have the localized covariance. In the middle, the static covariance BS that we will apply. And on the right, it's the hybrid covariance with 50-50 for both terms. But 50-50 may not be the best choice. So here it's an example where we have all the weight on the localized covariance and no weight on the static covariance. So it's 100 and 0. Here it's 75-25, 50-50, 25 and 75 on the static covariance, and all the weight on the static covariance. So we will have to find what's the best hybrid weight to get the optimal hybrid covariance matrix. And so I developed a theory for that because all the existing methods were empirical and costly. They were based either on brute force optimization or OSSE. And so we needed a method that would use only ensemble members, that would be affordable for high dimensional systems, and that would be generic enough to be run with all kind of grids. And so the principle is to see this hybrid covariance matrix as a filtering process, a linear filtering process. Basically, we have the ensemble weight and the localization weight that are like a factor applied to the sampled covariance, plus the static term, which is kind of an offset. And so both these operations can be looked at a linear filtering applied on the static and the sample B tilde. And so if it's a linear filtering, we can use the linear filtering theory to estimate the optimal weights and localization. So the asymptotic sample covariance here, B star, is our target. And so we want to reduce the residual noise, B minus B star. And the goal of this method is to express the hybrid weights and the localization that would minimize this error, the difference between the hybrid B and the asymptotic B star. And so we use the linear filtering theory, but some statistics will involve the asymptotic sample covariance, which is unknown. And the second step is to express the statistics on the asymptotic B with known quantities that are computed from the sample quantities. And so we use the centered moments sampling theory in a non-Gaussian case for this task. So I'll skip the details because it's pretty long, but you can have all the details in a note on the GitHub page of BUMP. But the localization, the optimal localization function alone, so here without hybridization, can be obtained with this formula. So here n is the ensemble size, and we have expectations of products of matrices, and the strange sign you can see on the right is actually the sample force order moment. It's because we have non-Gaussian statistics. We can also compute the optimal hybrid coefficients and the adapted localization for the hybrid case. And again, it's using the same kind of quantities. And so, as you can see here, there is no more star, there is no more asymptotic quantities. So it's all knowable or quantities that can be estimated with an ensemble. And so the training process to compute the localization and the hybrid weights, for BUMP, we will start by randomizing the static covariance, because we cannot specify a static covariance to BUMP because the static covariance can be very complex, have model-specific and generic operators mixed. So the easiest way is to randomize it, so apply its square root to a sequence of Gaussian deviates and get pseudo ensemble. And we plug this data with an ensemble of forecasts in the JEDI driver, and it will estimate and fit the localization functions and also estimate the hybrid weights. So this will provide the hybrid weights beta E and beta S, and also provide the localization length scales. And then we can plug these localization length scales into the NICAS driver to compute the smoother parameters and obtain the localization smoother data. So again, the orange box here shows the randomization process that can involve model-specific and generic tasks. And the yellow box is just the generic tasks that are done in BUMP. And in gray, we can see the localization and hybrid data obtained at the end of the process. For the local estimation of the localization with HDIAG, so we use the same process with a couple of points. And we will estimate the variance, covariance, and force order centered moment. And we will do a spatial and angular assumption, ergodicity assumption, to estimate the expectations. And that way we can replace the expectations that are in the formulas I showed before to compute the localization and hybrid weights. So here it's an example of what we get for a given local averaging center, the red point here, and we will average the quantities over the dark blue points in its neighborhood. And we can see that with all these couples, we get an estimation of the localization function. And again, we do the same process for many local averaging centers over the whole domain. And for each point, we have this raw localization function, and we will fit it with a Gasparian cone function. So here it's better because it's flatter at the top. So in general, the Gasparian cone function is good for localization functions for the fit. So we get the Gasparian cone function length scale, or its support radius actually. And so here is a summary of what we need to do, for the localization. So first we define a homogeneous grid. Then for each origin point, we find distant points for a series of distant classes. Then we average diagnostic values. We compute the localization and hybrid weights using the formulas I showed you before. We fit these localization functions with parameterized function, for instance, the Gasparian cone one, to get the localization support radius. And we can filter the localization and the hybrid weights over the subgrid. And finally, at the end, we interpolate the localization support radius and the hybrid weights over the model grid. Well, that's a long process, but at the end, we get maps of localization length scale and hybrid weights, which is what we need for a hybrid B that is not homogeneous. Here it's just a very simple example of the dependency of the length scale, the localization length scale, depending on the ensemble size. And what we can see here is that when we increase the ensemble size, the localization length scale will increase too. And it's what we expect because when the ensemble size is larger, we are more confident in the sample covariance we get. So we need less localization, and we can keep the values at large separation that are not affected with sampling noise anymore. And the second example is the variations of the hybrid coefficients with the ensemble size. And as you can see, the weight on the static covariance will decrease when we increase the sample size, and the weight on the localized term, so the ensemble term, will increase with the ensemble size because we are more and more confident in the ensemble term when the ensemble size increases. So it's basically what we expect. So just a summary about the ensemble A and hybrid B. So the sample covariance is affected by sampling noise. This sampling noise decreases if the ensemble size increases, but we cannot use huge ensembles. So we need to do some localization, and also, if we want hybridization, to filter out the sampling noise. The asymptotic sample covariance is our target, and we can combine both the filtering theory and the central moments sampling theory to get practicable formulas to compute the localization and the hybrid weights. Then we can compute robust estimates using ergodicity assumption, local ergodicity assumptions. And finally, we can get local estimates of the optimal localization, length scale, and hybrid weights. So the final theoretical part is about the Nika smoother. The main goal of this smoother is to design so a convolution operator that can work on any grid. So the other standard methods are just working on some kind of either on regular grid, or they have potentially high cost. So here I use an explicit convolution that can be working on any grid type and that have an exact normalization. But if I just use it, the explicit convolution as is, it will the cost would scale as n squared, where n is the side of the model grid, so it's not affordable. So to limit these computational costs, I approximate the convolution on a subgrid, so a subset of endpoints here. And the red S here is an interpolation from the subgrid to the model grid, and S transpose is its adjoint. And CS, the green operator in the center, is the convolution matrix on the subgrid. So it's a lot cheaper. If NS is a lot smaller than the model grid n, then the total cost scales as n, which is the model grid size. And so if we have some issues with this approach, because if the subgrid density is too coarse compared to the convolution length scale, then it will distort the convolution. And also the normalization will break down, even if the central operator is normalized. When it's interpolated back on the model grid, it's not normalized anymore. So the diagonal is not 1 anymore. So the Nikas method is this given by this formula, where we have this interpolated convolution, and then it's normalized to have exact ones on the diagonal. So to illustrate how it works, I'll give you some examples of an adaptive subgrid and show you the steps of a direct test. So the direct test is very interesting when we develop covariance matrices, because it's just applying a vector with zeros everywhere and a 1 at some point. And so we can basically get the columns of our B matrix that way. So here is the localization support radius, for instance. So we'll define a subgrid that is coarser on places where the length scale is larger, and with more points, for instance, here over Indonesia in the north, where the length scale is smaller. And here we start with our initial vector, so it's just 1 at some point. We apply a normalization, so it's maybe 1.1 here, something like that. Then we apply the adjoint interpolation. So since it's a linear interpolation in the triangle, the adjoint give components on the 3 neighbor points. Then we apply the convolution CS, so it's the convolution over the subgrid. So we start to see the final convolution function. Finally, we interpolate over the model grid, and we apply the normalization operator so that we have a perfectly normalized function at the end. So just as a reminder, here it's the localization support radius, so it's smaller over Indonesia here and larger over the Southern Ocean. And here is what we get for several Dirac functions. So we get broader responses in the south and tighter functions in the north. So that's what we wanted to have. The subgrid resolution is important. Here at the top, we have a quite dense subgrid, and we have very smooth and nice functions on the right. And at the bottom, we have a subgrid with a smaller density, so it's cheaper. It's a lot cheaper, but well, the functions that we get are a bit bumpy. So this subgrid density can be tuned with a single scalar parameter, and it's a good trade-off between cost and accuracy for the Nikas method. Also, since we control the grid and the convolution, we can apply a mask to this method, and so we can take complex boundaries into account, which is interesting for the ocean. And here it's an example of a comparison between the implicit diffusion method that is used in NIMOVAR. So it's an ocean data simulation model system at the top. And at the bottom, it's the Nikas method. So it's pretty close solutions, but the Nikas one is a lot cheaper. For the Nikas method, we want to have a square root, because it can be useful to randomize this matrix. So the square root is very simple. If we have the square root of the correlation operator on the subgrid CS, then it's very easy to have U tilde here, the square root. And we can also use the square root formulation to make sure that the matrix is positive semi-definite. And so it's easy to get the square root of the Gasparian cone function with just a multiplication with an empirical Scala factor. Okay, so finally, I'll talk about the BEM usage. We have a critical memory issue when we want to do the training with a lot of members. Here, for instance, I have ensembles of 80 members over maybe 25 cycles. And if I want to do the training computations directly, well, I got a problem because for the FV3 system, for instance, at operational resolution C384, one member is 11 gigs, one cycle of 80 member is 880 gigabytes. And if I have 20 cycles, well, it's about 22 terabytes. So it's pretty difficult to load simultaneously all this data on disk, and get them in memory is not possible at all. So the solution that I have in BUMP is to split the work and do some pre-computations for every cycle and store temporary data that are not small, but a lot smaller than a whole ensemble, and do a final training step just using all this temporary data, but not loading the members. So it was easy to do for the variance and the correlations, and required some developments for the regressions, but it's now implemented in the, so it's not in the current version of BUMP, but in the version that will be released very soon. And the other solution is to load members sequentially for each pre-computation. So instead of loading all the members, the 80 members at once, I can get the same results by loading the members sequentially. So finally, I just have to load members one by one, and it's a lot better for the memory footprint. So as I said earlier, BUMP is fully interfaced with OOPS, and the BUMP parameters can be set from a YAML file. And basically, BUMP works in two main steps. The first one is to prepare the BUMP operators, so it can require several execution of the estimate params.h class. And then once we have these BUMP operators ready, we can apply them in, for instance, a Dirac application or a variational one. Between the steps 1 and 2, the BUMP operators data can be stored either in BUMP-specific netcdf files when it's subgrid data, or when we have, for instance, the normalization fields that is defined on the model grid, we can have it stored in the model file format, which can be easier to handle. It's a typical YAML structure for the BUMP estimation. So we define the geometry, the input variables, the date, the background, the BUMP parameters. We define the ensemble addresses, and also we can have input fields for the BUMP file. For instance, the correlation length scales when we want to define the NICAS operator. And we have sometimes some output, for instance, the length scales when we compute the length scales from the ensemble. So to read the members sequentially, we just need to set the ensemble as an item of BUMP. So the difference is that ensemble here in the YAML file is indented. It's just a small difference. Well, the second question is how to apply, for instance, the static B when we have computed the operators. So in the YAML files, we need to set the central correlation operator first, and then define all the other operators as variable changes. So here in the background error, we define the covariance model as BUMP. We define what the correlation operator first, and then the standard deviation and the vertical balance are defined as variable changes. As I said before, we can also mix BUMP-based and model-based operators. So for instance, we can have here a model-specific covariance model, but use it mixed with a BUMP standard deviation or vertical balance. So it's completely free to to mix these different operators. So how to start? You can start by looking at two main examples, either in the QG model that is used for Sabre tests, for the unit test in Sabre, and also you can have a look at the FV3 JEDI system. So in the coming version, there will be a full static B-training provided. For the bump parameters in the YAML, you can have a look at this file here in the typenam file, where you have the default values and a short description of all the parameters. There is some documentation on the GitHub page, and you can get some support through the JCSD forum, the Sabre GitHub repo, or just my email if you need help.